Alright guys, in this video I promised you example problems, and I said listen, we've talked about this ranking order now, and we've looked at electronegativity, and we've looked at size, and we've determined how both of these at this point gives rise to which one could be a better acid. Without me looking up anything in a table, without me Googling anything, because Google doesn't have the answers to everything, right? So without me doing all of this, I can quickly look at structures and really just kind of pinpoint which one's going to be a better acid over the other one. Okay, I don't need any kind of resource material other than possibly a periodic table, and that's all I need. That's what's called the periodic table of the elements and periodic trends that are located in that table. So we're going to play the trends to our favor. So let's take a look at some example problems. All right, so here's an example problem. Which is a stronger acid? H2O or H2S? Okay, so it looks like a pretty simple question. I've got a 50-50 shot to figure out which one's correct. If you get this type of question on a test, do not leave it blank. Okay, you've got a 50-50 shot. That's better than the odds in Vegas. So come in, circle one of them, even if you don't know the answer, and just take a guess, and you might get it correct. I'm not going to know if you guessed or not. So don't leave these blank. Don't be silly. So which is a stronger acid, H2O or H2S? All right, so I need to go to the periodic table because the difference here is an O and an S. That's what's different. So I need to go to this table, and here we go. And here's the O, and here's the S. Notice that they are in different rows. Because of that, size matters. The bigger the size, the more acidic it is. And the reason is because hydrogen is further away from the nucleus. There's less glue that holds it together. They are not near each other. There's a little bit of room in there between them because the atomic radii is bigger. The attraction's not as large. So, what that means is that sulfur is going to be a better acid than oxygen, and that means that on this question, sulfur is going to be a better acid than the O. So I circled the one with S. That's all there is. That's it. You thought this was going to be hard, didn't you? Next one, which is a stronger acid, CH3OH or CH3SH? All right, so it looks like the difference here is O and S. Ah, that sounds familiar. Go back to the chart. O, S. S is bigger. S is further away. The hydrogen's further away in S. And because of that, there's less attraction. The hydrogen can be removed, making it a better acid. That's the same narrative we used last time. So the one with S is going to be a stronger acid. So I circle it. Folks, see, no one said chemistry's got to be hard. No one said organic had to be hard. This is all there is to it. Next, which is a stronger acid, HCl or HBr? Okay, so we go to the table. The difference is Cl and Br, so Cl is here, and Br is there. Br is bigger. Guess what I'm going to say? Br is bigger. Hydrogen's further away. There's less attraction between the two. Hydrogen can be spit off much easier, making it a better acid. Same narrative as the other two. So that means HBr is going to be the better acid. Once again, no one said difficulty exists here. That's all there is to it. If you can answer these questions, you'll do perfectly fine on this section of the test when it comes around. Here's another type of question. It comes kind of from your textbook, I think. A, we've already answered. I mean, that was in my previous example just now. But B, we've not. It looks like B is a little bit more complicated. There's more things that are written on a sheet of paper, but it doesn't matter. We still compare and contrast the same way. I know that there's positive charges there, but that doesn't mean anything either. Whatever. I mean, they both have positive charges, so who cares? What's the difference? Well, the difference here is an N and an O. So I'm going to go back to the periodic chart, and I'm going to look at N, and I'm going to look at O. Now, these are in the same row. So size has nothing to do here. Okay? Size is not going to be the determinant factor. What will be the determinant factor here will be electronegativity. So the higher the electronegativity, the more electron greedy, the easier the hydrogen is to be removed. So oxygen is closer to fluorine, right? This is the highest one, fluorine. As we go left-handed, it goes lower, 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 lower. As we go down, lower, 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 lower. But as we go left, oxygen is more electronegative than nitrogen. So that means oxygen is more electronegative, oxygen is more electron greedy, oxygen is more willing to kick hydrogen to the curb to get those electrons, making it a better acid. So in this example, the one with the O is going to be the stronger acid. The next one, they give you ball stick models. And then over here to the right-hand side, they're going to remind you what the colors represent. So they just want you to take the time and look at this model and compare it to what those colors are over here, just to get you acquainted with working with different types of molecule representations. That's all that this is about. A lot of people don't like this, but, you know, you could rewrite it if you wanted to. No one said that you couldn't. This black one represents carbon, and these white ones, they represent hydrogen. So this is a CH3, and then here's a carbon with 2 more hydrogens, and there's a carbon with 2 more hydrogens, and here's a nitrogen with 2 hydrogens. All right? And then here, we kind of do the same thing. CH3, CH2, CH2, and OH. If you want to rewrite it that way, be my guest. No one says that you can't do it. And now you look at the differences between what you wrote down. Well, here's a nitrogen one and there's an oxygen one. Well, you can quickly see the difference if you look at the ball and stick model. I mean, this is the difference right there. This is a nitrogen-based one. That's an oxygen-based one. Same deal, whatever. If you don't like these structures, write it to how you like it. No one says that you can't do it. So N and O. Well, this sounds like a similar story to from above. N and O. O is more electronegative. They're in the same row. More electronegative, more electron greedy. It sucks the electrons away from the hydrogen, and hydrogen goes, boop, off it goes, making it a better acid. So oxygen's more acidic than nitrogen, which means that this is going to be more acidic than this one. D, CH3, CH2, CH2OH, and then we also have CH3, CH2, CH2SH. The difference is O and S. On the periodic table, I go here, O and S. They're not in the same row. Electronegativity does not play a role. It's size. So sulfur is bigger. That means hydrogen is further away. There's less attraction that's there. And hydrogen can easily be removed compared to the O one. So sulfur is going to be a better acid than the oxygen. So in this question, I'm going to circle the sulfur-containing ones. Okay? More example problems. Look at these. Which is a stronger base? Oh, stronger base. Now they're trying to trick us. But do you remember what I told you to do every time that they do this to you? I told you to cross this out, and strong bases are weak acids. So this question wants to know which one is the weaker acid. That's what we need to do. So don't forget that rule. It's going to make your life so much easier if you can just rewrite it in terms of what you're comfortable with. And again, nobody says that you can't do that. So we'll just ignore stronger base and we'll pretend like they wrote weak acid in there because that is what it refers to. And now we can still compare to what we've been comparing all along, which is a weaker acid. So I get CH3O and CH3S. Okay, so folks, the way we do this, guess what? Same way as we did the others. No difference. O and S is what we need to compare. So I go to the chart. O and S. What did we do before? Oh, well, they're in a different row. Sulfur's bigger, therefore hydrogen's further away. Therefore, hydrogen can be easily removed compared to the O. That means that sulfur is a stronger acid. That's not what the question wants, though. The question wants which one's the weaker acid. That's the trick. So if sulfur is the stronger acid, that means that this is the weaker acid, the one containing the O here. So we got to think about this a little bit backward because we got to be careful on what they're asking. So this one is the weakest. All right, so for B, H2O or OH, which one is the weaker acid? Okay, so what do we need to compare? O and O? Well, we can't compare those, can we? They're the same. So that means we need to maybe look at this problem in a different way. We can't really compare two oxygens together. Which one is the weaker acid? Okay, so what this means is that water is H2O and the OH is OH minus. The definition of an acid is a proton donor. So which one of these would not be willing to give off the proton? Because that's the weaker acid. That's how we need to think about part B. Well, for water, it has a proton here that it can spit off. But the problem is that OH, it does have a proton too. If this hydrogen can be spit off and removed, that is the definition of an acid. But look, this is a negative already. If you are already negative in your bank account, do you want to be more negative? Probably not. So if this OH is floating around with already a negative charge full-blown on it, why would this species decide to kick off another hydrogen to make this even more negative? It's not going to want to do that. That hydrogen is a positive charge. It would kind of linger and stay behind at this point because opposites attract. Over here to the left with water, well, it's neutral right now. Because it's neutral, well, this hydrogen being kicked off is okay. Then it leaves behind a negative charge. Will it kick that second one off? No, for the same reason over here. So which one is the weaker acid? Well, it's going to be the OH minus. That's going to be the weaker acid here because it's already lost a proton. Why does it need to lose another? So it's going to hold on to it, which means that it's a weaker acid by definition. For part C, we're comparing O and we're comparing N. All right, so let me go to the periodic table again. N and O. Same row, size doesn't matter. We look at electronegativity. We said that O is higher electronegativity, therefore O is a better acid. But this question says weaker acid. So that means the one containing nitrogen is the weakest acid out of the two, and that means NH3 is the one that I'm going to circle. Next one for D. What do we do for D? CH3, C double bond OO, and then CH3O with a minus. At first glance, you'll look at this and you'll say, well, you know, here we have an oxygen and there we have an oxygen. So how does that really play a role? Am I comparing two oxygens again? That's kind of strange. And then this one has a C double bond O on it. So that's not really on the periodic table. The only thing on the periodic table are atoms. This is a whole group. So can we use the size or the electronegativity here at play? And the answer is you can. But what I want you to do first is not forget about something. And I don't want you to forget about tables that we have talked about in the past. So this is a C double bond O and CH3O minus. This is called an acetate, and this is called a methoxide. You don't know that. I don't want you to know that right now, but that's just what they're called. So this wants a stronger base. Well, let's use our resources here. Let's look at this table. If I go through and try to find my CH3COO, it's right here. Look at it. CH3COO. And I told you that was called the acetate. It's right there. This is just a condensed form of what they drew here. Well, let me go back to the slide. The C double bond O. Let me find that question again. Look at me. I'm scatterbrained right now. I've talked about acids and bases too much. Okay, so here we go. CH3COO. They just don't want to bother writing that double bond in that table because it takes up a lot of room. So they just condense this down and write CH3COO or CH3CO2. Either way is perfectly okay. So there we found that onto the table. And now we need to find methoxide. See if it's on here. That was a CH3O, right? So as I go down through, I'll kind of scan through and try to find something that looks like that. So I'm looking. Can't really find anything that perfectly matches. You know, here we have CH3, but it doesn't have the oxygen on it, and that's a pretty important piece. Here we have C2H5O minus. You know, this is close. It has an extra carbon and some extra hydrogens, but it's not a perfect match either. And then as I start looking at some of these others, I don't really see anything on here that looks similar to what I have, right? So I told you that there's going to be times where we can use this chart to our advantage, and here we thought that maybe we could have. But at the same time, I told you it wasn't a complete chart, didn't I? I said there's things that are going to be left off, and that's okay. I mean, this is not supposed to be representative of every acid and base known to man or woman. It's just the most common that we see most often. Okay, so it's not listed on this chart. The acetate was. So we were halfway there, but this chart's probably not going to do us any good. The other thing that I told you that we could maybe take a look at were pKa tables like this one. So pKa tables, we had OCH3, and we had the acetate, which is CH3COO. Well, as I go through, I could start taking a look at some of these different types of compounds. CH3O is really coming from CH3OH, and that is called methanol. And that pKa is going to be 15.5. Okay, 15.5 right there. Then if we take a look at acetate, this is going to be here CH3COO, and it's coming from acetic acid. That's 4.76. 4.76 is a stronger acid than the 15.5. But folks, I just did this to kind of keep you in mind of the resources that we've talked about. If you wanted to go this route, you could. And you would look at this and say, well, listen, carboxylic acid is going to be a stronger acid than methanol, or the OCH3 version. So because of that, this OCH3 is going to be the weaker acid out of the two. But let's take a look at that question again. So I've showed you the table. That way you didn't forget about it. I showed you the master table. That was a little bit more complete, so you didn't really forget about that one either. And then I told you there was a shortcut. That's something else that we've talked about too. Let's think about this for a minute. CH3, C double bond O, O, and that was an H there, right? We're comparing acids. So I want to write that H that's going to be there. And then here, CH3OH. I want to know which one of these two acids are weaker. The reason I had to do this is because the question was stated in base. That's why all of these didn't have hydrogens on them. You know, they had already lost the hydrogen. That's why they're all negatives all the way down the board except for waters. So I'm going to write the H here because we rewrote this to say weaker acid, and now these truly are acids, and we want to know which one out of the two would be the weakest. Folks, don't forget the other tidbit of information. pKa of carboxylic acids, C double bond OOH, these were around a 5. The pKa's of OH groups, that's an alcohol. These are around a 15. Based on the pKa's alone, the pKa of 5 is lower. Therefore, it's more acidic. And that means that this is our weaker acid. And that means this is the one that we circle. That is how we answer part D. So A, B, C, D that's here was really a representation of all the tidbits of resources that we talked about. Let's take a look at size. Let's take a look at electronegativity. We know functional groups for part D at this point. We should be able to go back into our Batman utility belt and pick out those pKa's and say, listen, we've got an alcohol and a carboxylic acid group here. We know that alcohols have higher pKa's. They are worse acids. Therefore, they are the weaker acids out of the choice that I have in front of me. So all of this, again, is going to start getting cumulative. And this is just, once more, the nature of organic chemistry as we do it. So this is where this video is going to stop. And in the next video, we'll truck on and we'll talk about substituents, which is one of those last groups that we need to talk about as far as acidity is going to get concerned. How do those other atoms attached to these molecules play a role in the acidity of a molecule and how it behaves? And that's what we'll talk about when you come back and see me.